Welcome back, participants. So, we are going to start our second lecture on this course. The title for this lecture is Design and Measure Emissions of Various External Combustion Engines by Professor Yang Wenming. I request, sir, to kindly proceed with his lecture, sir, please.
Okay, thank you. So we'll continue to introduce the second lectures. Just like we still have one last slides, but we can show you guys the last slides maybe by the end of this lectures. Okay, so let's go for the second lecture first. So in this part, we're going to introduce the design major missions of various external combustion engines. First of all, I want to introduce the steam engines. Here, show you how the steam engine works. So this one actually is a double entry steam engine. So you can see the high pressure steam, high pressure, high temperature steam can enter the steam engines from both sides. Firstly, we can see, so we can look at this graph. Okay, this one, so you can see actually, firstly, when the piston move from the left side to the right side, so you can see the high pressure, high temperature steam will enter the steam engines from the left side. So at the same time, we can see on the right side, the exhaust valve is open, and then the low pressure gas will be discharged from the engines, correct? So you can see because the pressure is difference between the left side and the right side. So this pressure difference will push the piston to move from the left side to the right side. And in this process, okay, we convert the thermal energy into mechanical power. Then when the piston move to the right side, and then the inlet valve from the right side will be open, and then the high pressure, high temperature steam will enter this engine from the right side. And then at the same time, the exhaust port will be open on the left side, correct? So again, the pressure difference between the right side and left side will push the piston move from the right side to the left side. Okay, so again, in this process, will convert the thermal energy into mechanical power. Okay, so you can see in this design, the high pressure, high temperature steam can enter the steam engines from both sides. So by this design, we can increase the power produced by the steam engines. Of course, there are also single entry designs. Okay, the next one, actually I want to introduce the sustaining engines. Let me show you a short videos. It is conducted by our FIP students. Okay, Yeah, so here we show you the steam engine works the basic design. So you can see there are two chamber or two cylinders. So this one, so in this one we can see actually the okay, we use the flame to the burner to warm up or heat up the gas inside this cylinder. Okay, so one question for you guys: do you know why is the working media for this steam engines? Anyone knows? Okay, actually, it's a working media for this steam engines is pure air with the pure air as a working media. So we can see what happened. So when the burner is used to heat up the air inside this cylinder, then the pressure, the temperature will increase, correct? Then the high pressure, high temperature gas will flow through this flow path and enter the second cylinder. Okay, so this high pressure gas will push the piston to move, okay, from the right side to the left side. So in this process, the thermal energy is converted into mechanical power, correct? Thermal energy converted into mechanical power. After expansion process, as we know, both the pressure and temperature will drop, correct? Then, okay, the piston will move back and push the lower pressure, lower temperature gas, push this gas back to the heating cylinder, to this cylinder again, and this heat up again. So this process repeated. Okay, so this process repeated. Okay, so this one is how the steam engine works. Theoretically, steam engines actually has the highest efficiency. In theory, can achieve the same efficiency as a Carnot cycle. However, in practice, it is its efficiency actually is much lower than that, because we know for this kind of engine, we can see the heat transfer depends on the power produced by this engine actually depends on the heat transfer between the burner and the working media inside this cylinder, correct? So you can see actually the heat exchanger error is quite limited. As a result, we know the power density will be very low, will be very low. So actually, steam engines is not is rarely seen in our practice in the industry in our daily life because the power density is too low. At the same time, actually for this kind of design, we can see actually quite a number of energy are wasted because the burner actually only small powerful heat engine transferred to the working media, and the rest maybe more than 80% of the heat engine is lost, is directly lost, correct? So the actual efficiency is much lesser than theoretical limit, upper limit. Okay, so this one is a steam engines. This one is the external combustion engines because we know the working media is pure air, and the pure air in the cylinder does not participate in the combustion process, correct? So the burning of the fuel and the working media are separate, okay, are different from each other, okay? So this one again is external combustion engines. Okay, the next one I want to introduce a biomass incineration power plant. This one is more and more commonly used in mega cities, used to burn the rubbish, used to burn the solid waste, and we can convert against the energy in the solid waste, in the rubbish into heat energy and into power, electric power. And at the same time, we can remove or eliminate the rubbish, correct? So it's very useful, useful power plant. Okay, so this one is a biomass and incineration power plant. So here we show you the schematic. Yeah, the major components actually is quite simple. First one, okay, this one is Okay, so the suppose rubbish will be collected and then delivered from here to the furnace. Okay, this one is a furnace, and this one is a grate. Okay, this one is a grate. So this grate actually can vibrate, and thereby move down. Okay, moves down the cause rubbish or solid waste. Okay, from the entry to the exit. And so this one is the furnace. So the fuel will be burnt in the furnace, and the heat actually will be released. Okay, then we can see actually we have a few heat exchangers. Okay, this one is superheater, and this one is an economizer. This one also is an economizer. All these are three different heat exchanger, three different system or heat exchanger. Okay, or heat exchanger. So when the flue gas flow through this path, then the heat will be transferred to the water and convert the water to steam. And then when the steam flow through the superheater, okay, the steam will be further increased, the temperature will be further increased. Then the superheated steam will flow through the steam turbine and drive the turbine to move. Okay, so in this process, the energy is converted into mechanic power. And again, okay, this steam turbine is connected with the electricity generator, so can further convert the the mechanical power into electricity. And also has some post processors. This one can help clean the exhaust gas, before discharging to the atmosphere. Okay, so this is also basic design and the working process. Okay, so I want to show you another video on this basic design and working process. Okay, so in this video, we show you how the biomass cogeneration system works. Just actually, I have introduced the schools of biomass and the incineration system working principle and basic design, correct? So this one actually is quite similar. So you can say actually you can use any types of fuel In this case, we use biomass, can be sawdust and any other solid waste. And also, of course, can use natural gas, we can use petrol, okay, the liquid fuel, correct? So here I want to introduce more steps. We can see actually in the this one is the furnace. So you can see the furnace actually from the furnace wall is consists of a water pipe, and so water will flow through the water pipe, and by this design, actually we can absorb as much heat energy as possible, correct? And minimize the heat losses to the external wall, correct? So when the water flow through the heat exchangers, then the water will become steam and become steam. And then the steam will further flow through the superheater. Okay, this one in the center part. Okay, this one is a superheater. Later we can see. So this is a water pipe. Okay, so when the heat and transfer to the water in the water pipe, the water will be converted into steam. Okay, this one is the superheater. Okay, so when the steam flow through the superheaters, the temperature will be further increased. However, the pressure will be the same. Okay, the pressure is not further increased anymore, only increase the temperature. Okay. Now we can see the high pressure, high temperature steam flow through the steam turbine and turn, okay, drives the steam turbine to move. So in this process, thermal energy is converted into mechanical power. And again, okay, this steam turbine is connected with this generator, so we can further convert the mechanical power into electricity. Okay, here we should be careful that, okay, by this kind of design, if we only produce electricity, then the efficiency is very low. Okay, you guys can guess how much the efficiency we can achieve the best one. As we know, for the coal boiler system, actually the efficiency is only about 40%, which means that we can only convert 40% of the chemical energy into electricity for coal boiler system. And the coal boiler system actually has a higher efficiency than this biomass boiler, than this course incineration system. Okay, much higher. For this kind of biomass, the efficiency may be only 30%. For this course rubbish, the incineration system, burning rubbish, then the efficiency will further drop to about 20%. Correct? So the efficiency is very low. Then how can we further increase the efficiency, improve the energy utilization? Okay, so we can use the course cogeneration. Okay, use a cogeneration. So you can see actually when the steam flow through the steam turbine, the pressure temperature will drop. However, okay, this steam still has high temperature, okay, basically more than 100 degrees C, correct? So we can use a heat exchanger to recover the waste heat from the exhaust steam, and then warm up the water in this flow pipe, and then supply to the CT. So we can we use this waste heat to warm up the house, correct? So by this design, actually we can improve the overall efficiency from about 30%, okay, from about 30% to more than 70%. Okay, thereby we can improves the overall efficiency from about 30% to more than 70%. Actually, it's the best design for the cogeneration for power plant, yeah, especially for the coal boiler system. Then the overall efficiency can as high as 90%. Okay, can as high as 90%. So cogeneration is a effective way to improve the overall efficiency. Okay, now we understand how the biomass power plant works. Okay, the basic design and also the working process. Okay, the next one, I want to introduce the major changes faced by the biomass boiler and incineration system. Okay, just like I mentioned, okay, when burning this kind of rubbish, its overall efficiency can drop to about 20%. So now we're going to discuss what are the major changes faced by the incineration system. First one is a high moisture content in biomass or solid waste. Okay, so water percentage in this kind of solid waste can be as high as 40%, 50%. Second one is the high ash content. Here, this picture actually was taken by us in the power plant, in the biomass power plant. So you can see the water pipe surface actually is covered by a very thick ash. Okay, so as we know, when the heat exchanger is covered by this kind of ash, the heat exchanger between the water and the hot gas will decrease significantly, correct? Thereby affects the overall efficiency, correct? Okay. The next one is the high emissions. Okay, high emissions. High emissions can be high NOx emission, high CO emissions, and high other types of harmful emissions like CO2, like the SOx. Okay, SOx emission. So all these are the changes faced by the biomass boiler and incineration system. The next one is a serious ash deposition. Okay, so here show you the picture, the ash deposits on the surface of heat exchangers. Okay, thereby affects the heat transfer between the hot gas and the water, or affects the heat transfer between the steam and the flue gas. And no efficiency, okay, the overall efficiency can drop to about 20%, okay, or even lower than 20%. And the next one is diverse in fuel quality. Yeah, if you look at this rubbish, okay, some of the rubbish actually has maybe a good heat has good heating value, and some other rubbish actually don't contain any energy, correct? So it is very diverse in terms of fuel quality. Some sand contains high ash, and some sand don't contains high ash, correct? So all this will affect the fuel properties and affects the combustion process, affects the efficiency. As a result, the combustion process become unstable. Okay, if you supply good quality fuel, then combustion process is very good. However, if you supply no quality fuel, then combustion process cannot be sustained. Okay, cannot be sustained. Okay, so these are all the major changes faced by the biomass boiler or incineration system. Okay, so now we are going to introduce how to evaluate the performance of the biomass boiler and the incineration system, and how can we improve the overall efficiency. Okay, so firstly, I want to introduce a thermodynamics model for heat losses evaluation. Okay, this model can help us to evaluate the overall efficiency of the biomass boiler or any types of power plants. So basically, there are 5 major heat losses in the power plant. Okay, so first one is the heat losses by the bottom ash or fly ash. Okay, by the bottom ash or fly ash. Okay, so we can see if you go back to the here go back to his this schematic. So can see actually after the fuse after burns, actually we still have part of the ash will be discharged from the furnace, right? And some of the fly ash also will be discharged from the boiler system. And when the fly ash and bottom ash discharge from the furnace, from the boiler system, actually they are still has high temperature. This is a few hundred degrees C, for example, 300 degrees C, which means that part of the heat energy is taken away by this bottom ash or fly ash, correct? Okay, so the first one is the heat losses due to the bottom ash and the fly ash because they are still has high temperature, okay, a few hundred degrees C. So they will take away a small part of our heat energy. The second one is the heat losses owing to incomplete combustion process. When the fuel is burnt and the flue gas discharged from the boiler system at this position, for example, actually not all the fuel will be burnt. Okay, you cannot ensure 100% of the fuel will be burnt. Okay, so in the exhaust gas still contains CO emissions. As we know, CO actually is a fuel, correct? Can produce energy by burning, correct? So the second one is the heat losses owing to incomplete combustion, which is the CO content in the exhaust gas. Okay, so the heat losses to the external wall. External wall, okay, just I mentioned, to the outer surface because in the furnace, in the boiler system, okay, we have high temperature flue gas, correct? Okay, we have high temperature flue gas. Also, the wall is insulated. However, even with a good insulation, actually on the external surface, the temperature is still higher than the environmental temperature. Okay, usually the external surface temperature can be 40 to 50 degrees C. Okay, 40 to 50 degrees C. Okay, as a result, we have heat losses through the outer surface, correct? Okay, by radiation, by convection, heat transfer, correct? So the heat losses due to the external wall by radiation heat transfer or by the convection heat transfer. Okay, the last one, the fourth one is the heat losses owing to unburned carbon, which is contained in the bottom ash and the fly ash. Okay, actually, when this bottom ash and the fly ash are discharged from the boiler system, this bottom ash and the fly ash still contains carbon content in the ash. Okay, thereby we also lose energy, correct? Because this is incomplete combustion process, incomplete carbon. Okay, so last one is stack losses. This one actually is a major heat losses through the exhaust gas, because we know when the exhaust gas is discharged from the boiler system, okay, usually the exhaust gas still have high temperature. Basically, it's about 200 degrees C. Okay, about 200 degrees C. So this exhaust gas will take away a lot of heat energy. Okay, actually, this Q5 is the biggest heat losses. Okay, so just like I mentioned, the fuel quality actually is very diverse. Okay, some of the fuel has a high ash content, some of the fuel has a lower ash content, and some of the fuel has a high quality, and some of the fuel has no quality. So we have collect the fuel samples at different timing. Okay, at different timing. Okay, for example, here we show you 13 samples we have collected at different dates. For example, the first one was collected on 18 April 2018. Second sample is collected in May 2nd. The third one is on August 17 and at different dates. Okay, so after collecting the samples, then we do analysis. Okay, we do analysis, for example, approximate analysis and the elements analysis. And also we test the LCV, the lower heating value. So can see actually the ash content is different. So we rank the ash content from lowest value to the highest value. Okay, from lowest value to the highest value. So can see the major composition also are quite different. Okay, for example, in this case, the carbon is 37% and the hydrogen is 5.19%, or oxygen is 28.48, and nitrogen is 1.53, sulfur is 0.04. So at different dates, the sample is collected, actually the major composition is different. And this one will affect the heating value, correct? Okay, so we rank the different fuel from lowest ash content to the highest ash content. Okay, then we do the test and simulation. So here's the foundation of the thermodynamics model for wood chip boiler system. Okay, so this is a line. Okay, red line is calculated value by using this model just I have shown you guys. The dot is a measured value. Okay, so this one is a comparison between the efficiency by using the simulation model and also by measured value. So can say actually the match with each other. So actually from here we can see we have connected more than 70, 80 samples. In this table, we just show you 13 samples. Okay, actually we have collected more than 70 samples and analyzed. Okay, so here we show you the efficiency for the boiler system. So the this Q1 the heat losses due to the incomplete combustion process, the CO content in the exhaust gas. Second one is due to the incomplete combustion. CO. Sorry, this one is due to Q1 is due to the bottom ash and the fly ash. Second one is due to unburnt CO. And the third one is due to the external surface, the heat losses to the external surface. And the fourth one is due to the bottom content, the bottom carbon content in the bottom ash and the fly ash. And the last one is the stagnosis. It is content in the exhaust gas. So we can see actually by comparing, so we can see. Okay, this one is a high quality fuel, medium quality fuel, and low quality fuel. Okay, and so can say actually the stack losses is the biggest one. Basis heat losses account for about 6.8% up to 8.2%. Okay, and the second largest one actually is this one external surface heat losses, and the third largest one is due to the bottom ash. Okay, only for the low quality fuel, the bottom ash, the heat losses to the bottom ash and flash has a greater value. Okay, so by analyzing the samples we had collected, we noticed that low quality fuel, about 35% of the fuel are low quality fuel, and about 30% of the fuel samples we collected is medium quality fuel, and about 35% high quality fuel. Okay, so here show you the average efficiency. Okay, high quality fuel basis efficiency is about 91%, and the medium quality fuel is 90%, and low quality fuel is 87.7%. Okay, in order to further investigate the major factors affecting the performance of the boiler system, also have conduct three-dimensional modeling. So here actually show you the how we create the model. So basically, this model consists of two parts. Okay, so first one is the fixed bed. This one we use as a one-dimensional model to simulate the fuel, the solid fuel, combustion process. Okay, so we simulate the drying process, devolatilization process, char oxidation, and ash cooling process. Okay, from here to here. Then in the free box, okay, we use a three-dimensional safety modeling to simulate the whole combustion process. Okay, then by combining these two, so first one, okay, this one can produce the boundary conditions. For example, the gas fuel compositions and the gas fuel concentrations and the temperature, okay, to the free box. Okay, this one produces the boundary conditions. Okay, for example, the fuel composition, the fuel concentration, and the temperature. Then supply to the free box to the safety modeling as a boundary conditions. Then in this safety modeling, we use a three-dimensional modeling to simulate the detached chemical reaction process, combustion process, heat transfer process. Okay, so this one is the safety modeling of the wood chip boiler system. So we can say actually, okay, this model is huge. Okay, this model actually has has 10 million and 10 million units, and also have measured the temperature at different locations. For example, T1 it is above the fixed bed, correct? And T2 is in the furnace, and in the lower side of the furnace, and this one on the top of the furnace, and this one is along the floor path, basically in the heat exchangers, and this one T9 actually is on the exit position. Okay, so we measure the temperature at different locations, and also we do three-dimensional modeling. Okay, so by using this numeric simulation model, we can basically simulate the flow streamline in the boiler system, and we can simulate the temperature distribution and oxygen concentration distribution, SOx concentrations, and NO concentrations, and also CO concentrations. Here we didn't show, but we can simulate all this kind of emissions. Okay, so firstly, we have validate the numeric simulation model with different fuel. For example, high quality fuel. The left one is the comparison between the simulation results and the experimental results. Okay, in terms of temperature. Okay, at different locations, just like I show you, we had 9 locations. We measure the temperature, right? Then this one's simulation results, and this one is experimental results. So compare these two. We found that the difference actually is very small. Second one also compares major emissions, for example, O2, CO2, NO, and SO2. And again, actually, a good agreement has been achieved between the simulation results and the experimental results. Next one, also we have validated the three-dimensional numeric simulation model for the media quality fuel. And again, this one is the comparison between the temperature. Okay, the temperature between the simulation results and the experimental results. The red one is the emissions, major emissions comparison. So again, we can say actually the simulation results is very close to the experimental results. Okay, the next one is the validation for the no quality fuel. No quality fuel means that the ash content basically is more than 30%. Okay, ash content is more than 30%, and the fuel, lower heating value of the fuel will be low. Okay, so again, so we can see a good match between the simulation results and the experimental results are achieved. Then we can use this model to do some parametric study. Okay, so after do the so-called a very comprehensive simulation, we found that we can take some measures to improve the efficiency. Okay, so first one, for efficiency improvement by adjusting the excess air ratio. Excess air coefficients. Okay, excess air coefficients actually is the air to fuel ratio. Air to fuel ratio. Okay, so we can see as we increase this the excess air coefficient, okay, from 1.2 to 1.6 plus 1.6. Then we can see the stack temperature will increase. This stack temperature will increase, which means more heat energy will be lost to the exhaust gas, and the efficiency will drop. Okay, so when you design the biomass boiler system, okay, you can try to reduce excess air coefficients. Okay, in this standard operating conditions, actually the band is 1.5. Okay, the band is 1.5. The excess air coefficient for the boiler system, the standard value is 1.5. But based on this simulation, actually we can further reduce this value to 1.2 or at least 1.3. Okay, thereby we can reduce the stack temperature and improve the efficiency. For example, we can increase from here to here. Okay, then we can see the efficiency will be increased by 1 point something. Okay, 1 point something. Okay, if the band is 1.6 and increase to 1.2, drop to 1.2, then the efficiency will be increased by 1.9%. Okay, 1.9%. Okay, this value looks very small, correct? 1.9 is not big issue, correct? However, if you consider the mega power plant, for example, 660 megawatts power plant, that 1.9 means how much? You can do a very simple calculations. Okay, you can save millions of dollars of money. Okay, every year. 1.9 actually is a big money. Okay, for the mega power plant. Okay, the second method we can take to improve the operating efficiency is to optimize the primary air distribution. Optimize the primary air distribution. This one is for high quality fuel, but optimize the primary air supply. The efficiency can increase by 0.03%, and for medium quality fuel can be increased by 0.29%. By for the low quality fuel can increase by 0.76%. Okay, so how to adjust the primary as distribution? Okay, so can go back to this schematic. So here we can see actually in the fixed beds and we have the air supply. Okay, this air supply is a primary air supply. Okay, so by increasing the air supply in zone 5, by increasing the air supply percentage in zone 5, then we can reduce the heat losses to the bottom edge. Okay. Okay, here. So you can see for the low quality fuel, the heat losses to the bottom edge actually is quite big. So 1.8%, correct? 1.8%. So by increasing the primary air supply in zone 5, then we can help to cool down the temperature of the bottom edge, correct? So by this way, we can reduce the heat losses to the bottom edge, okay? By increasing the air supply in this zone 5, okay? Then we can reduce the cool down the temperature, okay, of the bottom edge and reduce the heat losses to the bottom edge, okay? So by this way, we can increase the efficiency by 0.76% for low quality fuel, okay? Okay, so the method is for the fuel drying. Just like I show you, okay, the moisture level, case moisture level for the rubbish, for some of the biomass, actually is very high. Okay, here we show you the moisture level we collected, okay, from about 60, 70 samples. So basically you can see the moisture level, the highest one is this one, about 37%, okay, 37% of water, okay, and the lowest one is this one about 5.2 something, correct, 5.2%, and the average is about 24.5, about 24.2. So moisture level. So this one is for biomass. Actually, for some of the rubbish, the moisture level can be as high as 70%, 60%, or 70%. Okay, so even much higher than this one. Okay, so such a high moisture level will definitely affect the combustion process, correct? As we know, the higher the moisture level, the poorer the combustion process and the lower the efficiency, correct? Because water evaporation will absorb heat energy and bring down the temperature and affects the combustion process, affects the efficiency, correct? So we should try to minimize the moisture level in the fuel, okay, in the fuel. Okay, so we have do some simulation by pre-drying the pre-drying the fuel. Actually, for example, remove 5% of moisture, then we can increase the efficiency by 0.24% to 1.28%. If we can further pre-drying 10% of the moisture, then the efficiency can be increased by double. Okay, so increased by 0.68 to 2.56, correct? Okay, so last one for efficiency improvement is reducing the in-furnace pressure. Okay, actually in the furnace, the pressure is negative. Okay, the pressure in the furnace actually is lower than the surrounding pressure. Okay, it is not higher than external, than surrounding pressure is lower. Okay, but this pressure is only very slightly lower than the outside pressure. Okay, basically based on the simulation results, okay, this is minus 150 is the standard design, and if we can increase this pressure, okay, from minus 150 Pascal to minus 100 Pascal, then we can reduce the stack temperature, okay, and thereby improve the overall efficiency. Okay, improve the overall efficiency by 0.48, by 0.48. Okay, so that's the end of this is lecture 2. Any questions?
Yeah, participants, if you have any question, you can unmute your mic and can ask Professor.
Okay, yeah, if no question, I will, yeah, we still have, yeah, actually the time is finished already, but we Yeah, if you guys are interested, we can go back to introduce the structure uh, for the first lectures. Okay, so let me share with you this video. Okay, so in this video, I will show you guys the major components for the four-stroke gas engines, and also I will introduce a function for some of the major components. First one is the engine block. This one is the main supporting structure. Okay, this one is very simple. It's a crankshaft. Okay, so this engine, how many cylinders? Do you know? This engine has how many cylinders? 4 cylinders, correct? Because we have
Four
four
cylinders, sir.
pistons. Okay, great. Yeah, 4 cylinders because of four piston. Each cylinder has one piston, correct? Okay, great. Okay, now we have one question. Okay, pay more attention to this kind of questions. Okay, just like I mentioned, this kind of question can appear in the final examination. Okay, so what is the function of the flywheel? Anyone knows?
Sir, to carry out the three dead strokes means for example, sir, the suction stroke, compression stroke, and exhaust stroke, sir.
Mm.
First
Okay,
thing, and second thing is to carry the power means that is to carry out the momentum of inertia, sir.
yes. Okay, great. Yeah, very good. Okay, this flywheel actually is very important. Can use to store energy, because we have different stroke, power stroke, compression stroke, intake stroke, and exhaust stroke. Correct? Only in power stroke produce power. So we at the intake stroke, compression stroke, and exhaust stroke actually consume energy. Correct? So where's the energy come from? From the flywheel. Okay, so use a flywheel, which is obtained from the power stroke. Use this energy to drive the piston in the intake stroke, compression stroke, and the exhaust stroke. Correct? So can use to store energy, and also the second function is to keep the rotation speed, keep the engine speed is constant. Okay, otherwise, what happen? In the compression stroke, because consume energy, correct? Then the rotation speed will drop. Then in the power stroke, because absorb heat energy, correct? Oh, not absorb heat energy, absorb power, correct? Then the rotation speed will increase, which means that the car, if this engine is directly connect with the car, then what happened to the car? Okay, the car moving speed will fluctuate. Okay, sometimes very fast, sometimes will very slow. Okay, we also have this acceleration, deceleration, correct? Will fluctuate. So flywheel can maintain the rotation speed is constant. So we have two functions. Okay, this one is a cylinder head. Okay, cylinder head is used to install the screws of fuel injection system, ignition system. And also intake valve, exhaust valve also are installed in the cylinder head. So this one we can say actually is used. This is a camshaft. This camshaft is used to control the opening and close of the intake valve and the exhaust valve. This one is just a cover for the cylinder head. Okay, this one is the oil pan used to store the lubrication oil. Okay, this one is the filters can help to clean the lubrication oil. And this one is a starter. Okay, because we know before the engine works, okay, the engine is stationary, correct? The piston and the crankshaft is stationary. Then you have to use this electricity generate. Sorry, this one is an electric starter. So use this electric starter to start the engine, correct? Before the engine is self-sustaining. We use this electric generator to start the engine. Okay, this one is the intake manifold used for to draw the fresh air into the engine. Okay, this one fuel injectors. So you can see here the fuel injectors. Okay, this fuel injectors actually is installed close to the intake valve, correct? Because for gas engines, the fuel is injected into the intake manifold and premix with the fuel, then delivered to the engines. Okay, it's different from the diesel engines, correct? Diesel engines fuel is installed, fuel injectors is installed in the top. Okay, in the top, and in the center of the the cylinder. Okay, this one is a spark plug used to initiate the combustion process. So from here, actually, you can see this engine is a spark ignition engine. Okay, this one is a water pump used to power, the drive the cooling water to flow through the engines and cool down the core, all the most important parts of the engines, okay, to avoid overheating. Okay, this one is the air conditioning system. Okay, so you can say actually the air conditioning system for the vehicles is powered by the engine, correct? Not by the battery system. Okay, it's powered by the engine. That's why, yeah, if you want to turn on the air conditioning system, you have to start the engine first, correct? Okay, this one's electricity generator or alternator. Okay, this one is to produce electricity. And then we can use this electricity to recharge the battery system. Okay, so this one can use to recharge the battery system. That's why it's because you don't need to charge the battery frequently, correct? This one is exhaust manifold. Okay, so yeah, that's all I want to share today. Okay, yeah, any questions? We can yeah, take some quick questions maybe if you have.
Sir, I have one question, sir.
Mhm.
Sir, in EV also, electric vehicle, AC is also there, sir. But as you said, sir, the engine used to run the compressor, whereas means in that electric vehicle there is no engine. So how does the compressor work then, sir?
Oh, okay. Yeah. For EV, pure electric vehicles, of course, the air conditioning system, we use the electricity directly. Yeah, but for the normal combustion-based engines, we use engine to power the of course, air conditioning system. Yeah, because for the for the EV, so that's why the EV, you can see actually the battery system is huge. The battery system is very big in terms of size because they hope to store as much energy as possible.
Right, sir. But means we use a separate electric motor, yes, or something else, sir, to run the compressor. Yes, sir. We totally means eliminate the compressor and we use some certain special technologies here.
Okay, for the at yeah, I think the basic principle is the same. Okay, use as I use this electricity or use this cause other use this engine directly power. Okay, the principle I think more or less quite similar. Yeah, so but for this air condition system, I'm not very sure whether the working principle is the same. Yeah. Okay. Maybe in future we can discuss more. I need to search whether the air condition system is the same.
Thank you, sir, for
Okay, sir.
your nice presentation.